Hello again. Today I will talk about Deformable DETR, one of the newer and maybe harder to understand technologies. So here is an overcomplicated picture from paper about it. So a quick reminder of what that is and why we do it. So the last time we discussed the DETR model for object detection, and the one before that we discussed YOLO. So DETR is somewhere here on our roadmap of leaderboard of COCO detection. So it came out in 2020. It has something like 40 AP. So it's a bit behind other models that were popular at the time, like Original Proposal Network, YOLO, and so on. And so the most modern YOLO is somewhere here. But then we have this core DETR. It is currently the state-of-the-art model. And to build that, there is a lot of new stuff that was added to the original DETR. And one of those is Deformable DETR. So today we are talking about that. So here is the plan for today. First, we are going to discuss just deformable convolutions, which was the original idea that was later transferred into deformable attention. Then we'll talk about MultiScale attention and results. So let's start with deformable convolutions. So the idea behind deformable convolutions was to make it more effective to process images. So if you look at the left part of the image here, this is the picture for normal convolution. So we have our 3x3 convolution, and we've talked about before that you can apply several layers of such convolutions, and that causes the effective receptive field to increase. So in here we can see that receptive field for this point on the dog actually covers pretty much the whole dog. And it works. So it was actually proven that it works. Most of the modern models use that. But is it the most effective? So we can see that for the big sheep, for example, the same number of points is not enough to cover an entire sheep. So what we can do, hopefully, is to say that we can modify the points where we look depending on what sort of object we see. So maybe for smaller objects, we will have a more dense cloud of points. So we focus more on the details, we use higher resolution. And then for larger objects, we just scatter the points around more. So we don't need to look at every specific pixel because there is excessive information in that. But instead, we can cover more ground and recognize that effectively. So this is the idea behind deformable convolution. Let's discuss how exactly it was done. So first of all, how normal convolution works. This is the picture to the left. So we talk of sampling points. So let's say you have an input image. Input image is going to be in 3 colors, usually red, green, blue. And then after first layer, you would turn those 3 colors into maybe 32 channels, and then even more channels, and so on. So if you look at one channel, and we call that feature map, and you apply a convolution, you take the kernel, you keep sliding it over with specified stride, and each time you apply it to a certain position, you get 9 pixels from the original feature map. You have 9 weights of your convolutional kernel, and you just do the weighted sum of those pixels to achieve the pixel in the output. So the idea in deformable convolution is to have an extra trainable offset for every point. So we also start with this idea of just sliding the kernel along the image to get one reference point in the output. But then we also have these offsets, and the value of the offsets is trainable. So it will depend on the content of what we are actually seeing. And here is the illustration of our hopes of what can that achieve. So convolutions themselves, they represent translational symmetry. So if the object was here, it moved to here, we can still recognize it. But this is not the only symmetry that is actually present in the real world. So how about rotation? what the object moved slightly, or scale, when we just came closer to the object and the object became bigger in terms of pictures. So we hope that deformable convolutions, although they also don't have this symmetry by default, they can at least learn it. And here is how we are going to do it. So again, we start with input feature map, which at the very first layer is just going to be a certain color for the picture, and then at deeper layers it will be the actual feature map that comes from processing the image with a bunch of convolutions. So first we'll have this upper branch that is going to predict offsets. So it also acts as a convolution. So it has 3x3 receptive field. So we're thinking about generating this pixel in the output right now. So we look at where that pixel is in the input image. We have this 3x3 receptive field around it. And then we use it to predict offsets. So offsets, that's 9 pairs of numbers. So 9 x coordinates, 9 y coordinates, to say where exactly should you move this pixel in the receptive field. And we have an extra convolution predicting that. Then, when you have these offsets, the real convolution, the deformable convolution, it looks at this offset pixel locations and just performs normal convolution operation. So you have your kernel weights, you multiply them with the actual pixel content, you get your output. So now the main question is, how will this offset prediction branch of the layer work? That's interesting because it's not really obvious. Let's say we are going to predict integer values, right? So numbers like 1, 2, 3, and so on. We don't really know how to do that. So the output of the convolution or of dense layer is always a real number, so a number that can have fractional part. Then let's say even if we did predict some integer value, how do we select the points, the sampling points that we are going to use for convolution? We can say that, okay, I have predicted values 1 and 2, I take the offset to get the specified pixel, but then actually selecting that pixel is not a differentiable operation. So that doesn't sound like something that we can backpropagate through. So we need to find some sort of solution here. And the solution is two-stage. So first we predict real values, like 1.30, 2.71, something that can have fractional part. It might make it so that our sampling location are also real, so they might have fractional part. So we might arrive at some point that is not actually an integer, so it sort of lies in between the pixels. But then we use interpolation to get the actual expected pixel value here. And we hope that that will be more or less differential. So here is how we can think of it. Let's say this is our original image, and every edge here corresponds to a real pixel that has some value. So bilinear interpolation is actually a widely used technology. It's used pretty much every time when we need to resize an image after taking a photo on iPhone, for example. And the way it works is it looks at only the closest 4 points and then decides on an arbitrary value of any non-integer location between, based on how close this point is to every of these 4 reference points. So linear interpolation is really simple. If you have 1 point and a second point, and then a third point somewhere in between, you just draw a line between them and then deciding on that what should be the value of this third point. So basically, the closer it is to this yellow one, the closer the value will be to the value of the yellow point. And then bilinear is the same for 2D coordinates. So now you have 4 neighboring points, and you basically decide on the final value based on the value of all of them and the actual position of the black point that you're that you have. And so this is the equation from the paper. So now let's take a close look at that and see how we can make that differentiable. Now I have my point here that happened to be somewhere in the non-integer location, and it's close to some other points here. So thanks to Bilinear interpolation, the value that I should get from this point is now just a function of the 4 values of neighboring pixels. And so in mathematical terms, that is represented as this max function. So you can look at this one and see that it is indeed 0 for every point that is quite far apart, like this one, for example. And then for closest points, it will be equal to the actual distance, right? So this max function is not differentiable in the same way as max pooling is not differentiable. But we can pretend that it is differentiable. So basically, we are doing 2 operations here. So first, we select the 4 points that are closest to our non-integer location, and that part is non-differentiable. And then the second part is we compute this bilinear interpolation that is just a normal equation. We can differentiate it, we can backprop through it, and so on. So this is how we do it, and in reality, it does converge. So what we lose here using this method is the globality of this differentiation. So the point after computing the gradients, it might get pushed along somewhere closer to one of these 4 points during backprop, but it does not know what happens here, for example. So maybe the ideal location for this sampling point will be somewhere here, right? But we don't sense that because we only have selected 4 nearest points. However, during gradient descent, we can hope that it will move slightly here, then it might jump over here if the learning rate is high enough, and then eventually, after several steps, it will arrive where it needs to be. And experiments show that in reality it works quite well. So here is the demonstration of how these points actually look like for different reference points. So over here, the reference point is just somewhere in the background. So the network doesn't know where it should focus, so it's just sort of scattered all over the place to try and get as much area as possible to maybe understand what's going on here. And then in the case of this rather small car, all the points are densely packed together, so we can use more high definition information, more resolution within this area to recognize this small object. And then for bigger objects like this motorcycle here, the points are more or less focused around on the object itself and a little bit around it, but they are more scattered. So since we have limited number of points, we now can scatter them across, so we don't need every pixel in the picture because the object is big, but we can increase the area. And so these points represent the overall receptive field of several deformable convolutions stacked on top of each other. And this is another picture from the paper. Again, same story here. So when we focus on the background, they just scattered all over the place. When we focus on a small object like this sheep here, they're more densely packed together. And then for a bigger object, they still localize and cover mainly just the object, but they sort of spread out a little more to cover more ground. Right, so we have this cool idea of deformable convolution. And by the way, if you look at it, it sort of already looks like something like attention, right? Because we give our network the ability to decide which points to choose for sampling. Now let's talk about the actual deformable attention. So first, let's remember the usual attention from transformers. So compared to our previous pictures about deformable convolution, deformable normal attention can be viewed this way. So let's say we want to compute the attention mask for one point somewhere near the head of the bird. we'll have to go over all the pixels in the image to compute all the pairwise dot products of the embeddings. And we get this attention picture. So we always attend between every possible pair. That's a lot of points. That's why transformers are so computationally intensive, because this thing basically scales quadratically in respect to the number of pixels in the image. And that is the primary problem of transformers for object detection, because this makes us focus only on small resolution feature maps, because we basically cannot afford to look at high resolution. And that becomes a problem when we want to recognize small objects. So the idea of deformable attention is to do something similar here. So let's say we want to compute attention for this point around the head of the bird. Maybe on the first layer, we're just going to look at 4 points and let the network itself decide where those points should be, right? And then maybe after second layer, those points themselves will attend to something, and then the effective receptive area after a couple of layers should cover the bird completely, but then nothing else. So we give this extra ability for the network to decide where exactly to focus, instead of having to compute all those pairwise interactions. So again, a quick reminder how the actual transformers work. So before we feed in the image into the attention layer, we have to flatten it. So it usually starts with just an image, then we pass it through some convolutional neural network, which can be represented as this stacked cube of various feature maps for various channels. And then the actual pixel resolution is quite small, something like 20 by 20. And then we flatten that out into one giant sequence of these points within the image that we had. And this is how deformable attention will work. So if you recall, in normal attention, we had these 3 numbers, 3 layers to project down to query, key, and value. And we had computed pairwise interactions between all the query elements and all the key elements. So the main difference here is that we don't have a key. So we start with the initial sequence and we project that to queries and to values. That's in case of self-attention. In case of cross-attention, the sequences might be different. So we look at the query sequence and we just use an extra dense layer to project that down to a fixed set of numbers. So in our case, we want only 4 attention points. And for every attention point, we're just going to compute the x and y coordinates of the offset and the actual attention weight. So this is the main difference to the normal attention. So apart from limiting the attention weights to just 4 points, independent of the sequence length, we also make them independent of keys, right? So in normal attention, you would have query element of a sequence and key element of a sequence, and you will compute dot product for them. In here, you just look at the query and just decide on the attention weight using the query, not looking at the key at all. So this is one less interaction step that might spoil some things, but it still works. So we have this query sequence, we project that down to our offsets and attention weights, and then we do the same thing we did in normal attention. So for example, to compute this output element of the sequence, we look at some reference point where it was. Then we have our 4 computed offsets. So maybe one offset will say that we need to focus on ourselves. One will look at a couple of pixels around the current reference point. And when we use these 4 attention weights to get the weighted average, then we sum them up to get this one output sequence element. So this is how it works. And here is how the deformable cross-attention will look like. So once again, we don't have key, we just have query and value. And from the value side, we have our image, our encoder output that contains refined representation of the actual content of the image. And on the query side, we have our experts. And in Deformable DETR, we use 300 of them, which will correspond to 300 potential object predictions. And the output of Deformable Cross-Attention will have the same shape as the number of experts in the input, right? So now, again, the difference with normal attention is that we don't have the key. So in normal attention, we would have the key that comes from image sequence, and we have the query, and then we compute some sort of dot product between every possible pair of these. In deformable attention, we just have the query, and just use some dense layer on top of that to come up with the numbers for the attention weights and the offsets that we need. So we don't have this extra interaction with the image at the attention mask calculation step. Another problem that we need to solve here is how to come up with reference points. So now this output expert here, where should we start counting our offsets? So in self-attention, that was obvious. We just have the output pixel, and we just treat that as a reference point itself. And then the offsets will basically shift the actual attention a little bit up or down or left or right from this reference point. Now, query experts, they are not located in the same space as the image itself. So we need a way to come up with the reference points. And we use that by just applying an extra dense layer to query positional embeddings, right? So you can think of the sequence input as the target, the current estimation of predictions, and the query positional embeddings from the right. So at the first layer, the actual target is 0, and query positional embeddings are randomly initialized, learnable random vectors of parameters. And then after first layer, the target is going to be just whatever it was the output of the previous layer, and we still have these query positional encodings coming from the right. So we have these query positional embeddings. We use them to project an extra dense layer to decide on the reference point. And then we start counting our offsets from there. So now our offsets will tell that you need to look 2 pixels to the right, and they will tell you the actual offset, and maybe another one pixel to the left with the attention mask. And you use the weighted sum of these with the attention weights that you also got from your query to compute the output. So we have this extra step of also calculating the reference points based on initial query positional embeddings. So as you can see, there's quite a lot going on there, quite a lot of changes. So they might not look like a lot in code, but they change a lot conceptually, because now you have this extra reference points which basically indicate on which areas of the image this particular expert will focus. And we didn't have that in the normal DETR. So let's go over differences between normal attention and deformable attention once again. So normal attention computes all pairwise interactions for the attention masks. So it has quadratic complexity over the sequence length S. And because of that, we can't really process high resolution feature maps, which makes it hard to predict small objects sometimes. In deformable attention, you now have linear complexity. So with 4 reference points, you'd always have complexity of 4s. Because of that, you can process higher resolution feature maps, which helps recognizing small objects. Another big difference in deformable attention is that you are not using key embeddings. So you miss that extra step of cross interaction between one element of the sequence and another element of the sequence. You just decide on the attention mask based on one element. Now let's talk about MultiScale attention. So we're back to the original image that I had on my first slide, and we can now actually understand what's going on there. So MultiScale is a popular concept in different networks. So imagine that we start with an image, with a high resolution image, but then it will only have 3 colors. As you pass it through the backbone, through your convolutional neural network like ResNet 50, you would downsample it, reducing the spatial resolution, and then you would also increase the number of channels. So the final output of this backbone is usually a really, really small image, low resolution image, but with a lot of channels. But you can also take out the intermediate layer outputs as your final output. So in this picture here, we take the final one, which is the most processed. It went through the most layers, and then also a couple of intermediate layers. So they are less processed, they are more raw, they went through less convolutional layers in total, but they have higher resolution. Now, we could do multiscale with just normal attention, right? And we will do that by just flattening out all these three scales and just computing the full attention. So all the pairwise interactions between them. And it's just computationally infeasible. So you'd compute for a given feature map, you'd compute for every pixel, attention to itself, attention to other pixels within that feature map, to other pixels on other feature maps, and so on. It's just a lot of pairwise interactions. So the actual higher resolution feature maps would add a lot of complexity, and you also have this all pairwise interactions between all the feature maps as well. However, for our multiscale attention, that's not a problem. So once again, encoder input and output will have the same shape. So the input is this flattened representation of three feature maps. And then to get 1 point in the output, we compute a bunch of reference points for one feature map, and the attention weights a bunch of reference points in the second feature map, and the third one, and the third feature map, and so on. And we also do that for three output scales as well. The same way we did it for just one scale, deformable attention. And in the decoder, we also get our object queries coming from the bottom. We had our fixed encoder output that we call memory that gets passed in as a side input to all the deformable cross-attention layers. So now we have our object query. Based on the query positional embeddings of that, we first decide on the reference points. Then we compute the offsets to find out the actual pixels we're interested in and the actual attention weights. And again, we sum them up to get the new estimation for our query experts. So one last interesting detail here is that when we did the input, we had three independent feature maps and we just flattened them all out. So we've lost the spatial position information, so the position of the pixel within the image, and we compensated for that by adding a special positional encoding. We also lost the level information. So we had three scales before, and we knew which pixel comes from which scale, which level. Now we flattened that all out, so we've lost this level information, and we want to add an extra level encoding to let the network compensate for that lack of information. And in practice, as a level positional encoding, we just use a learnable randomly initialized set of parameters. So in the model reported in the paper, they used 4 feature maps with different scales, and that ended up being like 20K final sequence lengths. It's like 20 times bigger than the original DETR had, with about 800 sequence from 20 by 20 image. So once again, encoder input and output have the same shape. We also need this extra level embedding, which we just use as a learnable vector. Other than that, it works. So that was it. I hope my explanation was clear. So now I want to spend a couple of minutes to tell about the results and about what we will do next. So this is the image from the paper that showcases the quality of the model they got from Deformable DETR as compared to normal DETR, how fast they can train it. So the x-axis here is the number of training epochs. And we can see that Deformable DETR certainly trains faster. This last step you see here comes from step learning rate scheduler. So it's a curious way of doing the step scheduling where you wait for 400 iterations until the precision starts to saturate, and then you do one step of dividing the learning rate by 10. That causes you to go up a little bit, but then you saturate again. And for deformable DETR, they do that for various step sizes, for various periods of this step learning rate scheduler. But overall, we can see that the entire curve is much higher. So we train faster and achieve better final result. And then the actual final one is something like 2% average precision better than the baseline, which is quite a lot. Certainly enough to attract attention along in the scientific world, certainly enough to have good publication, but then it's still far from the state of the art that we know today that has 66 average precision. So obviously that one will have a lot of additions in it. So we have like 50% faster training, 2% final multi-average precision. Inference is also faster because we have less these attention points that we need to compute. And in most of the transformer-based object detection models that came out since then, we also use deformable attention as the main attention component. So in future models like dynamic anchor boxes, denoising DETR, which is called Dino, the co-DETR, which is the current state of the art, all of them use deformable attention. And next, I wanted to talk about what there is in my channel and what sort of video I'll make next. So I want my channel to be more of a path that you can start somewhere not knowing much and then just follow this path to learn what you need. And so we started with a really simple task of digit classification with PyTorch that you can get done in half an hour just following the tutorial online on the PyTorch website. Then we threw in a lot of stuff written down here. So convolutions, activation, Xavier initialization, optimizers, momentum, learning rate scheduling, loss functions, image transformation and data augmentation, and so on. So if you don't know some of these words, maybe it will be useful for you to check those videos out. Then we had our first big project where we looked at the actual implementation of ResNet model, which is also used as a backbone for modern transformers. So this is a big model. It takes like a couple of weeks to train, 150 gigabytes of data. And we did that ourselves using our own computer. Then we moved on to object detection, where we now have several objects in the picture. We need to localize them. We need to predict bounding boxes. We discussed YOLO to do that. We discussed DETR. Now we are on our way to current state of the art. So today we have discussed deformable DETR. Next one will be reading the actual source code of the official implementation of deformable DETR. Then we'll look at other models that also contributed to improving the overall quality, like dynamic anchor boxes, denoising, Dino, and so on. At the same time, the very next video that I wanted to do will be about generative AI. So this will be the very start of generative AI. It branches out from about 2015 when the ResNet was trained. So if you just know this, it should be enough to understand the first pieces of it. So we'll start with neural style transfer, which is a cool technique. It's not really the coolest that is there at the moment, but it has some important concepts that will be needed later. So I'll start with that. Then we'll talk about unconditional image generation using GANs, diffusion, variational autoencoders. And that is when you can just click a button and the network outputs some random image. You can't really control what is there. It basically just depends on the training data that you have. And then it will take a lot of time to build the foundation that we need to be able to tie up the text description of an image and the image itself. And we will use that both for basically object detection, where we let our network, we train it using textual descriptions of scenes, and then the network might detect objects. It's called open set prediction, where the network predicts objects that it didn't see in the training set, maybe. but you just say that I want the third sheep from the left, or maybe something that the model was not trained on, like a brick, and you can just describe that in text, and the model will find that for you. And in reverse, we will use that for text-based image generation, where you have the actual prompt of what you need, and the model generates an image according to this prompt. So stay tuned, and I hope to see you soon.